Hi, I'm Nathaniel, and I'll be going over my research on using GAN-generated adversarial examples to harden a DGA detection model's ability to detect unseen malware variants. So first I'm going to go over some background information on DGA malware. So most modern malware, such as bots, Trojan downloaders, and remote access tools, need a way to communicate with the server owned by the attacker to properly function. For example, a bot needs to be able to communicate with an attacker's command and control server to receive commands from the bot master, such as to carry out a DDoS attack. In the case of a downloader, it needs to be able to connect to a server that it can download additional malware from. So overall, having these servers are very important to the functioning of this type of malware. Now the attacker also needs a way for their malware to know the address and then communicate with this server. So the simple solution, hard coding a list of server domains or IP addresses in the malware, could work, but this would make their malware vulnerable because if these addresses are discovered, they can easily be blacklisted or shut down. And in this case, the malware could still be active on the device, but it would have no way to communicate back with the attacker. To get around this, malware started using domain generating algorithms, which use a starting seed to dynamically generate a list of domains. So for example, malware could be programmed to use one of these algorithms to generate a new list of 10,000 domains every week, using the date as a starting seed. Then it could attempt to connect to each one of these domains. Now the attacker could in advance generate this list using the upcoming date. Then they could register a few of these domains as command and control servers. So that way the following day, when the malware generates and attempts to connect with the same list of domains, it will eventually hit one of these command and control servers. Now security-wise, this presents a problem, because now even if these addresses were eventually discovered and shut down, the next week the malware could simply generate a new list of unblacklisted domains. So here are some examples of domains generated by real malware. So due to having to be algorithmically generated, and because they don't want to collide with real domains since they can't be registered, these domains often don't look too realistic compared to actual domains. Due to this, there's been previous research on detecting these domains based on character level features such as valid constant ratio and domain length, as well as deep learning approaches which use the domain string as an input, and we'll be focusing on this deep learning approach for this research. Now the other main element of this research is GANs, or generative adversarial networks. So this is a deep learning algorithm made of two networks that are trained together, a generator and a discriminator. So the generator is trained to transform random noise into real looking samples, and the discriminator is conversely trained to be able to differentiate between samples produced by the generator and real samples. And then by training both of these competing networks together in a series of rounds, the generator will get better and better at producing real looking samples that can fool the discriminator, and the discriminator will be better and better at being able to tell the difference between real samples and samples generated by the generator. So previous research has investigated using domains generated from a GAN to increase a DGA detection model's ability to detect unseen DGA families. So this research, called Deep DGA, used an autoencoder-based GAN to generate adversarial samples, which were then used to harden a feature engineering-based random forest model. Building upon this concept, we test a similar experiment using an improved GAN and detection model. For the GAN, we train a gradient penalty Wasserstein GAN, using benign domains as an input, which produces a set of generated domains that are difficult to differentiate from real domains. The resulting set of domains have characteristics, such as character distribution, that more closely resemble real domains than sets produced in previous research. We then use these GAN-produced domains as additional examples of DGA domains and use them to augment the training set for a DGA detection model. So while a feature engineering approach has been used in previous research, we use a deep learning, CNN, and LSTM-based detection model, which had significantly higher holdout detection rates for many DGA families. After training, we evaluate the model by comparing its detection rate on holdout DGA families with GAN augmentation compared to the same model which used an unaugmented training set. This is shown to increase the detection rate of the classifier at a standard false positive rate on certain DGA families. Further, unlike previous approaches, we conduct significance testing on the resulting detection rates to more accurately show the effect that the adversarial hardening had on the model. So now I'm going to go over the architecture of the models that we used in this research. In previous research, models that utilized LSTM and/or CNN layers were shown to have the highest detection rates, so we based our GAN model on a similar architecture. The CNN layer should help the model be able to learn combination of characters that make an inputted domain more likely to be real, and the LSTM can then learn the relationship of features in relation to their sequential occurrence in a domain. Now for the objective function of the GAN, we used Wasserstein GAN with a gradient penalty due to its benefits over the standard GAN function. Other GAN objective functions, such as KL divergence and JS divergence, can suffer from vanishing gradients when the generated and real distributions are more disjoint. This can lead to the gradients of divergence being close to zero, which would cause the generator to learn nothing during gradient descent. This is combated by the Wasserstein loss function, which is based on Earth mover distance. This causes the objective function to have a smoother gradient and be differentiable almost everywhere, preventing the vanishing or exploding gradients seen when using KL or JS divergence. This allows the generator to still learn even if it's performing worse than the discriminator. Further, the function uses a gradient penalty term that penalizes the deviation of the discriminator's gradient norm from 1, which softly enforces the function to be Lipschitz 1. Now for the detection model, we primarily wanted to measure the effect of augmentation, so we created a model based on past successful architectures, where LSTM and CNN-based models performed the best. So this model has a similar architecture to the discriminator of the GAN, but we used a sigmoid output rather than a linear unbound score used in the GAN, and we also used an embedding layer rather than one-hot encoding. So for our datasets, we had a benign dataset, which was made up of the Tranco top 1 million domains. So this is similar to other popular sets, such as Alexa. However, it's designed for use in security research as a whitelist, so it's more stable and has malicious domains removed. And then we use the top 100,000 domains in this set. For our algorithmically generated domain set, we used reverse engineered DGA algorithms from 14 malware families and generated 10,000 domains for each family. So to generate samples from the softmax output of the generator, we used weighted random sampling to choose a character for each of the 63 positions of the domain, when this produced domains like this sample. The boundary between valid characters and the padding character would often not be perfect, so we just created the domain by splitting on the first occurrence of the padding character. And then from the resulting domains that had a length of 4 or less were dropped due to their high collision rate with real domains. So here's an overview of the testing setup for a DGA malware family. So since we're measuring the detection rate on unseen DGA variants, we completely hold out samples of just a single DGA family from the training set, and then all other families are used for testing. We also set aside 15% of our benign domain set, so we can standardize the trained model to have a false positive rate of 1 when we measure the detection rate on the holdout DGA family. We perform 10 runs for each DGA family, and in each of these runs we train 2 identical models with the same base training and testing set. But we augment the training set of one of these models with GAN-generated domains as additional examples of DGA domains. So here are some samples of domains generated from the GAN, and visually we can see that the generator was able to capture the character combinations of real domains. This caused the generated domains to take on some of the qualities of real domains, such as having character combinations that are pronounceable. To analyze these domains more technically, here are the character distributions for the generated domains compared to the benign dataset. And we can see that overall the generated domains were able to fairly accurately model the real domain set in terms of character distribution. This distribution also showed a significant improvement in similarity compared to the domains produced by the GAN in the DeepDGA paper. This similarity also occurs in the length of the generated domain set, where we can see that our generated domains were able to fairly closely match the length distribution observed in the benign set. For each malware family, we ran the experiment 10 times, then performed a paired t-test on the true positive rates of the augmented and control models at a standardized false positive rate. And in the table, the detection rate differences with a p-value of less than 0.05 are bolded. And you can see that at higher confidence levels, GAN domain augmentation was able to have a significant increase on the detection rate of the model. While we tested slightly more malware families, our LSTM and CNN-based model had a higher control and augmented detection rate than the random forest used in the DeepDGA paper, with only 3 of the 10 common families tested having a lower detection rate by our classifier. We can observe a potential pattern in the data if we plot the relationship between the domain length and the error rate reduction of the GAN model versus the control model. This gives more weight to the improvements made at higher true positive rates, allowing the results to be better compared. And then we can see that GAN augmentation appears to have a lower detection rate on DGAs that produce shorter domains, where 4 of 5 DGAs that had a decrease in accuracy with some significance had an average length of 11 characters or less, while all improved domains had a length of 11 or more. So in summary, we have shown that a LSTM and CNN-based Wasserstein-GAN gradient penalty model can be used to generate real-looking domain names that outperforms previous research. We test the effect of augmentation using a deep learning-based DGA detection model, which has higher detection rates than the random forest model used in previous research. And then we also showed that GAN augmentation was able to increase the detection rate with significance on several DGA families. So thank you for listening to my presentation, and now we'll be moving on to the live Q&A session.